Okay, so this is the graphical explanation of the equation for Rayleigh flow. So if you look at here, there are three sections. First of all is for Mach number bigger than 1, which is supersonic flow. During heating, the Mach number will decrease, but when cooling, the Mach number will increase. That means when heating, the velocity will decrease, but when cooling, the velocity will increase. So, when heating happen, you will finally reach the maximum value of entropy. So I forgot, this is temperature against entropy. So we will reach the maximum value of entropy. So at that point, that the value of Mach number is equal to 1. And afterward, this line is for Mach number lower than 1, which is the speed is subsonic speed. This is the different. This subsonic speed can be divided into two sections, which is this one, the first one, and the second one. So what is the difference is when when the temperature is increasing, or during heating, the temperature will increase, yes. But after some point where Mach number is equal to 1 over square root k, when you do more heating, the temperature will decrease. So from B to A, the temperature decrease. So this is the behavior for Rayleigh flow, where we consider heat transfer with negligible friction. So let me read this one by one. All states that satisfy the conservation of mass momentary energy equation as well as the property relation are on the Rayleigh line. So entropy increase with heat gain, and thus we proceed to the right of the Rayleigh line as heat is transferred to the fluid. So we are going to the right hand side where the entropy increase. Heating increases the Mach number for subsonic flow but decreases it for supersonic flow. So heating increases the stagnation temperature TO for both subsonic and supersonic flows, and cooling decrease it. So entropy increase with heat again to point A. Entropy increase with heat gain to point A, which is the point of maximum entropy, MA equal to 1. Okay, so they didn't describe this section, but this section is important. Where after this value of Mach number, when heating continue, the temperature will decrease. Okay, let's go back to the slide. Okay, so this is the one that I'm showing you. So we go to the next subtopic, which is adiabatic duct flow with friction. So right now we don't consider the heat transfer anymore, but we consider the friction, and we call this Fano flow. So friction must be included for flow through long duct, especially if the cross-sectional area is small. Friction is often negligible for flow through short device with large cross-sectional area. So here we study compressible flow with significant wall friction, but negligible heat transfer in ducts of constant cross-section. So there are two types of flow, Rayleigh flow and Fano flow. So it depends on the situation. If the diameter is small and the friction is significant, so we use Fano flow formula. But if the the heat transfer is significant and the friction is negligible, we can use Rayleigh flow instead. So what is the definition of Fano flow? Study one-dimensional adiabatic adiabatic flow of an ideal gas with constant specific heat through a constant area duct with significant frictional effect. So this is the formula, a little different, where in the energy equation there is no additional heat applied, but in the momentum equation we have friction component right here. And the rest is more or less similar to one another between Van der flow and Rayleigh flow. Again, I want to show you the graphical description. So this is the Rayleigh flow I showed you just now. So this is the Van der flow. So this is much simpler because there's only two sections, 1 and 2. This one is for supersonic flow, and the upper one is for subsonic flow. So what is the difference? Let us read this one by one. Practical approach is to assume various values for T2 and calculate all other properties as well as friction force. So in here there's no heating. There's no heating in Van der flow, but what is appear is the friction force included in this diagram. So this line is the locus of all physically attainable downstream states. So if there's no heating, we can consider it applicable for any stream state. Entropy increase with friction to point of maximum entropy. So when the Mach number is decreasing from supersonic, actually the friction is increasing. It's worked the other way around. When subsonic speed is increasing and reaching the Mach number equal to 1, the friction will increase, and finally it will reach the maximum entropy where Mach number is equal to 1. So we have two branches only, 1 and 2. So okay, let's go back to the slide. This is the table which describe the change for these parameters: the velocity, Mach number, saturation temperature. So for and the rest. For temperature, there's only decrease and increase. And if you look at here, all is opposite to each other except for entropy and for stagnation temperature and also stagnation pressure. So you need to, you don't have, I don't think that you need to memorize this, but you need to understand these two flow, the Van der flow and the Rayleigh flow. So this is the tutorial that you can do to have better understanding. So that's all for our lecture for week 4. Thank you for listening. I hope you understand and practice with the tutorial and example so that you can prepare yourself for the coming examination. Okay, thank you very much. Assalamualaikum.